My topic today, the possible role of MI coupling in substorms. I'm sorry to say I've never looked at an ion and thought very much of one, and so and so sorry. But at any rate, I thought that I would try and pound a square peg into a round hole, because what I really talk about is MI coupling. And really? No, it's solar wind magnetosphere coupling, but it's not really magnetosphere, because what I look at is the magnetic perturbations on the ground. And a magnetic perturbation depends on the conductivity, and it depends on polar cap potential and things like that. And so maybe through an analysis of how the solar wind controls magnetic activity, I might be able to see some effect of the ionosphere. Now, you heard a few minutes ago from Lynn how difficult it really is to find real evidence for ionospheric effects of all these ion outflow. I went through the literature, and the first that I found was a Coronadian Kennel back in '72, line tying in the polar cusp. Then George Reed started talking about impedance mismatch, the alphane impedance of waves coming down when you turn on reconnection or fluctuate it, and its impedance mismatch with the polar cap. Then Akasofu talked about field-aligned current closure and feedback processes with ionospheric conductivity. Dan Baker talked about faster tearing mode growth if oxygen was present, but I heard people talking about slower reconnection when it was present, so I don't know what the truth is there. Saturation of the polar cap potential, we know it really exists and has a significant effect on electric fields. Ion outflow mass loads convection, reducing speed. That was Wing Lee. Then we heard about the neutral wind flywheel. You spin things up and it just keeps going, even when you turn off the driver. Bill Lotko has talked about plasma sheet O+ lowers reconnection rate, requiring either more frequent or stronger substorms. And then Brambles talked about the sawtooth. Basically, load the field lines, stretch them out, pinch them off, send out a plasmoid, and start all over again because you're driving it so hard. Can we detect these ionospheric effects on substorms? Well, does the type of magnetic activity depend on them? You heard a little bit about that. Pseudo breakups, isolated substorms, and so on. Is the frequency of substorms affected by ionosphere? Is the strength of substorms affected? And that's what I'm going to talk to you about today. In fact, it's pretty hard to do any of these things, because what is a substorm, what is its onset, how often do they occur, and so on becomes a little hard to define. The usual measures for us that study the coupling are polar cap index. That's basically just the magnetic perturbation of a sheet current that has been calibrated against the solar wind electric field. The AU index, that's the eastward electrojet in the afternoon sector. And the AL index, that's two things. That's both the DP2 in the midnight region, and it's also the DP1 as you get the substorm current wedge formed. So these are the three standard measures that we use. We also have DST, but I'm not talking about storms. I'm talking about substorms. Well, some of my researcher friends appear to believe that the indices do not exhibit systematic quantitative relations to the underlying phenomena. They basically say that you can have just about anything out for the same conditions in, or vice versa. And there are multiple reasons for that impression, that basically they're worthless as quantitative measures of activity. But what else do we have that has 50 years or more of data, of the entire history of the solar wind measurements? They depend on time of day because of station location. The indices depend on the day of year because of Russell McPherron effect or the equinoctial effect. distance of the Earth from the Sun, solar zenith angle. The indices depend on phase of the solar cycle because of UV radiation. They depend on the way high-speed streams and IMF sectors evolve on the Sun. The indices depend on the strength of the solar wind driver. So you can see that there's a lot of reasons that you might come to the conclusion that indices don't tell you much about the ionosphere and how it's affecting the magnetosphere. Here is a map of the hour of day versus day of year. Now, we know that magnetic activity supposedly shows a semi-annual variation. This is spring and this is fall. But look at the UT variation here. Well, as you go around, you have stations at different locations relative to the currents. And so this is what the AL index actually looks like, a gigantic peak at around 16 UT. The equinoxes. And this is what the AU index looks like, 2 peaks, but all peaked around midsummer. So we have to we don't know how to take out this effect of the station distribution. And in fact, it changes with the strength of activity because of the size of the polar cap. Okay, I'm going to be talking to you about coupling strength. How strongly does the solar wind connect to the currents that we're measuring around? And of course, coupling strength you can think of as the ratio of the output of the system to the input under steady state conditions. And of course, that's nanotesla per millivolt per meter. That's what we're going to be talking about. Here is day of year now, solar cycle phase for 4 solar cycles. That's almost 50 years of data. These are hourly averages. This is AL index and this is the AU index. Now this is coupling strength. And the surprising thing when you look at AL is the coupling is strongest at solar minimum. Now the activity itself is strongest at solar maximum at the edges, but the coupling strength, the output for a given input, is stronger at the minimum of the solar cycle. Here's the semi-annual variation of geomagnetic activity with peaks close to the equinoxes. Here's AU. It's pretty much just active all the time in the solar cycle, stronger at solar minimum and the rising phase, but again, I'm sorry, that's day of the year, but it's also strongest near just in the rising phase. Well, coupling functions are what we use. We're not really using electric field. We're using a coupling function that has been normalized so it has the same cumulative distribution function as the electric field has. We have functions like the universal coupling function that's V to some power, B transverse to another power. This is the gating function depending on the clock angle and so on. I'm going to be using a function called the optimum function, which is optimal, and it's about 2% better than the universal coupling function. So here's what makes it have the same properties as the electric field. Here we've normalized it to the average over the solar cycle. It's almost squared. As you may remember, a Slavin and Holzer paper for years ago that came up that, Murayama and others. B transverse to 0.8 and sine to the 3.1. That's the coupling function I'm using. And a technique that I use is linear prediction filtering. Basically, it says when you're looking at a dynamic system, the current output depends on the current input and preceding inputs. So we'll do it in a linear way. The current output is a linear sum of weighted sum of previous inputs. That is called the prediction filter. This is the relationship at one instant of time. Think of it as many instants of times. That creates a long vector of outputs. And this matrix here is actually the time-shifted input. So what we're after is this filter, which we can do by basically inverting this matrix. We know output, we know the input, and we determine the prediction filter. And this problem, of course, is the system is nonlinear. So what we do is simply bin the data. we say we'll only use data in a certain range of the driver strength, and we'll make a linear approximation and get this coupling strength and so on to see how it depends on various parameters. There's two things I want to use: prediction efficiency. It's what fraction of the variance in the index is this coupling function able to predict. Varies from 0 to 1, actually from negative infinity to 1. And the other is the coupling strength here. Coupling strength, since a system is never stable, you have to get it through the impulse response. And if you just stick a constant into this equation up here, you will find that the you can take the constant driver outside, and you just get the constant times the area under the impulse response function is the coupling strength. So that's what I'm really using, is the area under these prediction filters. To give you some idea, this is 1995 through 2013. It is 688 prediction filters in cycle 23 and 24 for the AL index at 15-minute resolution. And this is for the AU index at 15-minute resolution. These are lags in 15-minute intervals. And you can see that there's a wide range of variation around the black line there. That's the average. And look at this rather peculiar behavior of the AU index. It has this sort of Gaussian spike at just a 15-minute offset, superimposed on some sort of weak Rayleigh function in here. And again, this has sort of a Rayleigh behavior. The peaks are around 15 to 30 minutes. Okay, what I've done is I've calculated the area of those prediction filters for the entire time that we have high resolution data, 95 through the current time. That's a solar cycle plus. This is the coupling strength for the AL index. It's strongest coupling at solar minimum. And here we are, and then we come down to the solar maximum. It isn't the weakest coupling at solar max. It's a couple of years later as we begin the declining phase. Then we started to build up, and then we got into trouble. We call it the anomalous solar cycle 23. And all of a sudden here, and I'm going to tell you that it should have gone right back up to a peak, just like it had been here, but it turned over and started doing other things. The blue lines are the difference between equinoxes and the solstice. There's quite a large seasonal variation, semi-annual, and this is the annual variation in the AU index. Now, there doesn't seem to be much other than a progressive decrease in the last cycle in the AU coupling. I've gone back using hourly data, which is easy to do, to 1963, calculated the prediction efficiency, and you can see I'm getting 70% of the variance in the hourly data. That's really pretty good, saying the system is driven by the solar wind. Notice these the area, that's the coupling strength, maximum at solar minimum, drops again, maximum, drops, and so on in that sawtooth fashion until we got up here. And then look at blue and red. Those are the coupling functions, universal and optimum, and it just drops out. So it's something anomalous. AU doesn't display much of a solar cycle variation. So a very significant one in the AL index and a very poor one in AU. This is annual variation, minus 182 plus 182. This is using the hourly data again for 4 solar cycles. And look, let's just skip the details up here, but come down to the coupling strength, semi-annual variation. But notice this, winter is weaker than a summer in coupling. That's got to be an ionospheric effect that's entering into this. Here's the AU index. No evidence at all here of the driver and its semi-annual variation. It is completely an annual variation in the AU index. So if you start mixing them together as AE, you've got very different behavior in the solar cycle and in the season. So that's not a good thing to do. What is causing the solar cycle variation? And well, the only idea that I had at first was it might be F10.7 and ionospheric conductivity. But it goes the wrong way. I should have had the highest conductivity and hence the largest disturbance at solar max, but I don't. It's the other way around. So I got thinking about the effects of polar cap saturation, and in particular, AL index, as you drive the system harder, moves up on this saturation curve with the slope is the coupling strength, and you see it gets weaker and weaker as you drive stronger and stronger. So my hypothesis was that I'm looking at the increased number of strong driving events at solar max, which weakens the apparent coupling. That's my hypothesis. So here is the saturation formula, the Hill-Cisco formula, and this is what the slope looks like as a function of the saturation electric field and the driver. George, in his paper on this subject, here's the baseline conditions that he used, and you can see the saturation and the polar cap potential, the driver of AL. And you can see that if you increase the dynamic pressure by a factor of 10, it goes way up in terms of the saturation. If you increase the conductivity, you saturate much earlier. So it ought to depend on conductivity and dynamic pressure. Well, there's hardly enough data to do this at high driver strength, let alone separate it by dynamic pressure and the conductivity. But at any rate, this is what the saturation curves would look like. This is what the coupling strength should look like as a function of driver strength. By the way, that number is 210 times electric field, and the saturation value I got was 12 millivolts per meter. Well, I have done the driver strength dependence. Now, what do you mean? I'm using that curve, remember, that goes up. I bin the data into a certain bin of driver strength. I calculate the prediction filters, and then I change the bin. And here's the driver strength. And you can see in here where my bins are centered. And you can go in from 0 to 20 millivolts per meter. Here's the driver strength as a function of driver strength. It's a linear function, of course. Here's the AL index going up, and it saturates almost. But here is my coupling constant that I've calculated. Now notice, it actually goes to infinity at 0. That's probably because I have no driver and things are blowing up. Then at first, as you drive it harder, the coupling strength gets larger until you meet the saturation curve, and then from then on, it drops off. And prediction efficiency is very low when you start binning like this, and I don't get up to anywhere near the values I had before. But notice that the AL index looks like it's a little bit larger than it should be in here for saturation, a little bit lower than it should be, and so on. And the question is, what's going on there? Well, come to AU. AU goes up, it looks like it starts to saturate, and turns over and goes down. I didn't know that. I've never heard anyone tell me that AU index, as you drive the system harder, essentially goes away. And when I try to get a saturation curve here, fitting this lower part, you see that it's going to 0. That's 0 in terms of coupling strength. Prediction efficiency is doing weird things as I get it down to so little data. Well, what are my conclusions? The conclusions are that we can see in the form of the change in the coupling strength with season that there are seasonal effects that are coming out of the conductivity of the ionosphere. And we see it in both AL by the weak minimum at summer solstice and the strong one at winter solstice. We see it in the AU index by being exactly peaked. I think that we are also seeing the effect of polar cap saturation, which is again a conductivity effect in a way, that by the way that we are modulating the AL coupling strength with the solar cycle. But I sure didn't see a single ion in doing this. Thank you.
Not sure I ever saw a linear prediction filter I thought much of either.
I was thinking of you, Tom.
All right. Nice talk. I have a question and a comment. The comment is about AU going down. My grad student Roxanne Cadis had a paper about a year ago that looked at statistical clustering of a bunch of different indices, including AU, and showed that it indeed goes up in the early main phase of intense storms, just like a moderate storm, and then in the late main phase it actually nosedives. So I invite you to look at that paper.
I will.
But the question I have is about your time series plots where you were highlighting the last 5 years or so and saying that it's anomalous. It's saying that your coupling strength tanks or something, but the tanking was actually in the same direction as the other solar maxes.
But it did 3 years early.
Yeah,
what you couldn't see in that. So
you're saying that the solar max actually happened 3 years early?
Yeah. That was 2008 was my solar minimum on there. So about 2005, the interaction began to change, and the peculiar thing is this has got something to do with the distribution of electric fields and magnetic field strengths, velocities, and so on in the solar wind, because the electric field went right up to its maximum like it should for AL at coupling strength, and then it fell off. But the other two turned over much earlier. And they depend. The interesting difference between E, solar wind, and the other coupling functions is BY. BY does not enter into the electric field coupling. It does enter into the other. So that's the only clue that I have.
Could the dipole tilt produce the seasonal modulation that you see in the coupling efficiency?
Oh, yes. In fact,
I mean, that doesn't have anything to do with conductivity or the ionosphere.
No. And neither does, remember that the equinoctial, the semi-annual variation is attributed primarily, it used to be to Russell McPherron, and then to the equinoctial effect. Equinoctial is tilting the dipole towards and away. Russell McPherron is tilting it orthogonally. The best estimates of Cliver and Svalgard was 10% or less for Russell McPherron and most of the rest. My estimate is 30% for Russell McPherron and 70% for the equinoctial effect. Hasn't got anything to do with the ionosphere.
So, but I guess I missed you. You were saying that you were looking for an ionosphere conductivity effect to produce a seasonal modulation in the coupling efficiency?
Yes, my seasonal modulation peak at the equinoxes, minima at the solstice, but the minima in winter is much deeper than the minima in summer. So there's an annual variation in AL coupling, strongest in summer, just like there's an annual variation in AU that's strongest in summer.
But can't be produced by dipole tilt.
Yeah. I can't see how it would be. It should be symmetric, if anything.
Bob, since I'm responsible for asking you to give this talk, can I ask a couple of things related to ions? Does the plasma sheet have any role in substorms? Well, this is a two-part question. Number one, does the plasma sheet have any role in substorms?
Well, the answer to that is there are 4,400 papers dealing with substorms, and almost all of them talk about.
Suppose the plasma sheet was dominantly filled from the ionosphere with mass coupling. Would you say the ionosphere plays a role in substorms?
Oh, sure.
Good.
The problem, though, is the problem is the percentage. And that's what I'm thinking about with Lynn and her talk, is that if it's only fractions out there, yeah, it'll have some effect, but we probably won't be able to detect it in these coarse measures that we use.
Yeah, but Lynn was talking about O+, and it's important, certainly, but then there may be a whole lot of H+, a whole lot, that's going out and making the plasma sheet.
Oh, Well, for all I know, that's where it all came from. But I don't believe that. But
Well,
it
so-
could be.
Okay.